The recording started.
I see. Thank you. Thank you. Okay, yeah. I think I'm gonna start, if you don't mind. Well, I'd like to welcome everyone to our seminar series. It is my pleasure to introduce Mr. Aris Kanellopoulos. I hope I didn't chop your name.
That was pretty good.
But also, I'd like to thank him in such a short notice to accept our invitation. I'd like to say a few things about him. Aris was born in Athens, Greece. He received a diploma in mechanical engineering from the National Technical University of Athens in 2016. In 2017, he was a research assistant with Professor Kevin T. Crofton, Department of Aerospace and Ocean Engineering. By the way, there is this department is named now under Professor Crofton's name at Virginia Tech. Currently, he's pursuing his PhD, working with my colleagues and friend, Professor Kyriakos Vodakis, and working as a research assistant at the Daniel Cunningham School of Aerospace Engineering, Georgia Institute of Technology. His current research interests include cyber physical security, game theory, optimal and learning-based control. Soon he will be a doctor, and wish him a good luck. Thank you so much. So the floor is yours.
Well, first of all, thank you for having me. It's a pleasure to be able to share all of our ideas and see what people have to say about them and get your valuable feedback. So let me get this started. All right. So you should be able to see my screen, right?
Yes, we do.
All right, great. Well, again, thank you for having me. And well, first of all, if at any point anyone would like to interrupt me to ask anything, just please do. And I will try to keep this as concise as I can. And I'm going to talk to you about our work related to cyber-physical human systems. I think you will find interesting. And I'm going to talk about how we have tried to bring different ideas from different sciences by using tools from control theory and game theory in order to make such systems more secure and safe while they operate with alongside humans. Now, first of all, just a quick outline of this presentation. Initially, for those that are not familiar with the types of systems and the types of problems and the open questions that there are in the field, I will go through some motivating examples and some issues that we have to deal with in the integration of those systems to society. And then going into the technical part, I'm going to talk about our work in implementing and introducing moving target defense principles for cyber-physical systems through control theory. And then I will spend a lot of time talking about a main topic of our research, which is on bounded rationality. This is a game theoretic concept mostly, and we're going to see how we can employ those results in differential games, first of all. And then going a little bit deeper into security instances, we will show how we can use something called the cognitive hierarchy approach for an instance of cyber-physical security for sensor network. And finally, I'm going to talk about our current work, which is more into the dynamics of the learning mechanisms and how we can use those in order to employ intelligence approaches to dynamic deception. And finally, I will talk about some of our ideas for the future research directions that we can take with this project. Now, without further delay, first of all, I've been mentioning cyber-physical systems quite a lot, and I'm pretty sure that a lot of people, especially in this crowd, are familiar with what those systems are. But just to introduce the rest, they are complex platforms comprised of physical and a digital layer. Now, that pretty much covers every kind of engineering system around, but what's special about cyber-physical systems is that the physical and the digital realms are very tightly interconnected in such systems, right? So they have issues that need to be explored from a software engineering perspective and from a physics and control-oriented perspective. Now, as you can see in the examples that I have here, the applications and the fields where we can find such systems are very safety critical. We have such systems in healthcare and medicine. We have pacemakers that are connected to various software applications. We have instances in the aerospace engineering field, which, I mean, the obvious one are drones with different levels of autonomy and different levels of communication with human elements and different levels of interaction with human elements, both collaborative and adversarial, which is a main topic in our research. We, of course, have the automotive industry with all the raids happening right now regarding autonomous cars. And of course, we have some issues in energy efficient buildings that have autonomous subsystems that try to optimize different components of the building. Now, however, the complexity of those systems raises security concerns. The fact that they are so close to humans means that we have to be very careful that nothing can go wrong, either by accident or by someone trying to manipulate the system in some way. Okay, so again, the complexity that we have here renders the classical defenses inadequate. Right now, having, for example, software defenses, right? Probably antivirus systems, for example, it will not be enough to completely secure a drone because the wing might break off. The antivirus system will not help with that. So we need to have a more holistic approach to what's happening in a cyber-physical system. Furthermore, as you notice in the title of the presentation, we have to take into account the fact that those systems are, as I mentioned, very close to human elements. They have penetrated civilian life, they have penetrated military life. So now they are basically, they can be manipulated by humans, which are both unpredictable and adaptive. And furthermore, we all know that we have those artificial intelligence and learning mechanisms that are integrated into autonomous systems right now. So we have to really delve into security and safety issues regarding those components. I think, well, of course, there are a lot of examples of attacks and faults that have led to destruction, basically, in cyber-physical systems. The most recent of which happened actually where we are right now in Georgia, with the shutdown of a US pipeline, of the Colonial Pipeline, by a cyber attack that was a few months back. But throughout the recent years, there have been a lot of attacks. So this is not a theoretical issue right now. It's quite practical. We have had pacemakers being recalled because they can be hacked online. We have had, well, the first one, and probably one of the more famous ones, is the Marucci at Maruti Sire in Queensland, the cyber attack there, and we have had hackers using bubbles, changing the pressure in pumps that are able to destroy the pumps themselves. We have had attacks in chemical plants, and obviously, and that's actually interesting because there's a lot of talk about this in even layman publications. We have had very, very hackable autonomous cars. So those are all issues of security and safety that we need to address. Now, in trying to put our work specifically into context, again, this is very important. We operate in extremely human-centric environments. We have people and autonomous agents acting together. They can act in a cooperative fashion and they can act in an antagonistic fashion. One way to take this into account is to create prediction models that the autonomous agent will be able to employ to have the decision-making mechanisms account for what a human might be able to do. This is very important for the military as well. That's why one of our projects, the Minerva Initiative, has been interested in modeling human behavior for analyst training, that people that will operate alongside those cyber physical systems. Now, the mathematical tools that are mostly used in this field is decision theory, although decision theory is more of an umbrella term, and the specific mathematical topics that we take into account are static optimization problems, their optimal control problems, and their game theoretical problems. Now, those fields are extremely huge, and there are innumerable results in those fields. However, one of the underlying assumptions, especially in a lot of applications, is that everything is perfectly rational. All the agents are completely optimal in their behaviors, and everything is predictable, and everyone knows that everyone else is predictable. Which brings us to the scope of our work. We're trying to circumvent those assumptions, those very limiting assumptions. So we propose methods of securing cyber-physical systems against adapting and realistic opponents. Towards this, we introduce notions of unpredictability, mathematical notions of unpredictability for dynamical systems, and we're trying to see how different components of a system, such as sensor and actuators, can be defended against attackers. And furthermore, we investigate, as I mentioned, models of prediction. We investigate models of intelligence that will be able to give us prediction of what people will be doing. Again, in this regard, we use bounded rationality principles, and we try to bring those to cyber-physical defense frameworks. Now, if there are no questions about the general scope of our work, I'd like to move into the first of our topics, which is moving target defense for cyber-physical systems. Now, again, since we're talking about, you probably can imagine that the issue of security is so deep and broad that a lot of different communities have delved into issues of securing systems. Now, we have a lot of different approaches, either them being system-wide with abstract games between abstract defenders and abstract attackers. We have had network security approaches where people have talked about trust over networks. They have employed network topology alterations. We have had information theoretic centric approaches, well, obviously encryption and cryptography, but also we have POFs, physical unclonable functions, and frequency hopping. And of course, we have control theoretic security, which is a bit of a more recent field where we've had passivity-based and H-infinity-based controllers. We have had adaptive control, and we have had the estimation of various parameters to predict their behavior. Now, as we can see, there is something very interesting here. In network security information-centric approaches, there are ideas of proactive security, making the system harder to attack instead of just defending or shielding it or making it more robust, right? So our idea is to fill in this gap. to introduce proactive dynamic frameworks in control theoretic security. And our main principle has been this. A constantly changing system makes it harder for the attacker to find the best attack strategy. We're trying to take a system and make it as unpredictable as I can. So in principle, an attacker will not be able to find the parameters of their optimal attack. Now, going into the mathematics of this issue, we have considered linear time invariant systems in continuous time. Most of our work has been in continuous time so far. With very general models of attack. We have an attacker that is able to input, to manipulate the control system of the cyber physical system, and we have attackers that are able to manipulate the sensor measurements. The goal remains the classical control theoretic goal: regulate the system, but now in the presence of actuator and sensor attacks. There are two things that we will be introducing here. As I mentioned, the first one is a proactive defense framework with the principles of moving target defense. We will be switching in a stochastic and in a probabilistic way between different modes of operation of the system and different parameters in an effort to optimize the uncertainty of the system, the unpredictability of the system, while keeping the optimality of its behavior as close to optimum as I can. And furthermore, we will introduce a reactive defense framework that is just a classical intrusion detection mechanism, which, however, has been inspired by principles of integral reinforcement learning. So the evaluator is not model-driven, it's performance-driven. Now, putting it all together, we have a system, as in here, we have actuator attacks and sensor attacks between the plan. We have a switching logic that will act as our proactive defense that will shift between different controllers or different components of the system. And we have a reactive defense framework in the intrusion detection scheme. Now, as you might have guessed, in order to be able to switch between different between different operating modes of our system, we need to have redundancy. Redundancy is a key point in what we're doing here. And of course, we know that this is quite natural in cyber-physical systems due to their large-scale nature and their complexity. Asking for more sensors or asking for more actuators is not strange. So redundancy is something that we need. So we have sets of controllable actuators and we have sets of observable sensors that are able to completely drive or completely observe the system. One of the standing assumptions here, and this is not as strict as one would think, and it's also quite natural, is that the attacker cannot compromise everything at once. If the attacker has access to all of our channels, all of our components, all of our sensors and actuators, there is absolutely nothing we can do. So this is an assumption. The attacker is not omnipotent. Now, the way that we're going to start by talking about the actuators, and most of our presentation will be about actuator attacks. But what we have now are different sets of actuators. We know that by using those different sets, we're able to completely control the system. And in this case, we choose a very simple LQR controller for each of those different actuators. So we have a system, we have a bunch of different LQR controllers with that utilize different actuators. And what we're going to do is we're going to introduce a probabilistic switching rule among those subsets. So each controller will be active with a specific, at every time instant, will be active with a specific probability given by this expression. Now, it's important to notice the components that this expression have. We have the total cost of its controller, which is how optimal a specific mode of operation is on its own. This is encoded by the value function of the controller. We have a weight on the unpredictability. This is where we introduce the notions of the uncertainty and the unpredictability of the system. And by tuning this parameter, we make the system more or less unpredictable. we of course need to have this redundancy that I've been talking about. We have a number of candidate controllers at each time step over which you use. Now, this expression is not random, obviously. It's the output of an optimization problem that guarantees a balance between the optimality of the operation of the system and the unpredictability. And this is just a simple static optimization problem where we know that the cost of the unpredictability is encoded by the entropy induced by the probabilistic switching rule, by the probability of the actuator being active. Now, of course, once we're talking about changing the system all around, we need to be very careful with what the effect will be on the long-term operation of the system. So we have investigated the asymptotic stability of a system utilizing the moving target defense framework, which we have published in TAC. Now, the standing assumption is that we have the switch system with the optimal feedback by the various modes of operation. We have different matrices and different Riccati matrices, both actuating matrices and Riccati matrices for each of those modes. And what we do is we claim that by changing the system with a dwell time, so staying at a specific mode of operation for at least that much time given by this expression, then the closed loop system has an asymptotically stable equilibrium point. And the reason we went with, for those of you that are wondering why, because there are different ways that you can prove stability in switch systems, the reason we use dwell time is to decouple the stability issue with the probability simplex itself, the solution of the optimization problem. So even if I want to make the system more unpredictable or less unpredictable because I know that there are no other attackers in my environment, I won't have to investigate its stability again. If I keep this bound as it is, the system is good to go. Now, moving on to the reactive defense, and we'll see why this has been important as well. We'll see where the MTD fails and where this model-free intrusion detection comes into play. We, as well as every other detection mechanism, we introduce a detection signal. Now, this detection signal measures the state of the system over a specific time interval. Now, for those of you familiar with reinforcement learning or integral reinforcement learning continuous time specifically, you will recognize that this is nothing but an integral version of the Bellman equation. This is something that gives me consistency over my optimal behavior. So now, this has been inspired by the integral reinforcement learning framework, and we have a detection mechanism that's based on optimal behavior rather than explicitly the system matrices, which means that in using this system in tandem with reinforcement learning algorithms, we should be able to have a model-free detection system. Now, again, going into the theoretical underpinnings, we have a theorem that this detection signal is both necessary and sufficient to detect an attack on an actuator. Now, putting it all together, we propose a system, a cyber-physical system, where the proactive moving target defense mechanism is constantly active. So we keep switching between different modes of operation to make the system as strange, as unpredictable as we can, while at the same time we have a detection signal for the active mode based on the integral Bellman equation of the system. What happens now is that if a compromised mode is identified, so if my detection signal shows me that a specific mode has been attacked, it is taken out of the switching queue, and we'll see how this and why this is important. And afterwards, the system just keeps working with the moving target defense framework over the reduced candidate set. Putting it all together again, we have shown asymptotic stability under the MTD switching with the integral Bellman intrusion mechanism, And using the assumption that I've mentioned before, we need to have at least one uncompromised mode. If everything's been taken offline, there's not a lot we can do with our framework. Now, just going through, just quickly going through a simulation example based on the benchmark aircraft Admire, which has redundant sensors and actuators. We have switching between the controllable subsets, and we have the detection mechanism operating. But let's see what happens when we have the MTD working for the specific system. We can see, for example, that in this scenario, it just happens, if you take a look at the switching signal, that the fourth operating mode is the one that's employed the most, which means that based on the optimization problem that I showed before, that it is the one that's more optimal. And we see that the system eventually does converge to zero. However, yes, as I said, the switch signal favors the optimal controller, and given the dwell time analysis that I mentioned before, the system is asymptotically stable. There are specific trade-offs, however, that we need to take into account. We know that as the entropy increases, we reach a maximum expected optimality loss that's given by the uniform distribution. So at every time step, the probability is equidistributed between the different modes of operation. And we can see that there is a trade-off between this increase in unpredictability and the optimality. So we see that we have a higher optimality loss the more unpredictable we get, but by launching random attacks into the system, we can see that there is a huge decrease in successful attacks over the system. So we need to take this trade-off into account. Now, where the reactive mechanism, the detection mechanism come into play is in cases where somehow the most optimal mode has been taken offline. We can see here that we are operating under the MTD framework, and the system keeps switching, but we can see that eventually the system is not stable. We can see here that the controllers try to mitigate the damage, but eventually they fail. So now, by using the idea of the reactive mechanism, by taking the compromised components offline, we can see that the NTD framework keeps operating over the rest, the reduced subset. And we can see that in this scenario, by taking the bad controller, let's say, out of the queue, the system does converge to zero. So yes, as I said, we detect the attack and we take the compromised controller out of the queue. Now, I want
a question.
Yes.
May I ask you, can we go back to previous?
Certainly.
Sorry to disrupt you. Now, when you're switching many times, what I see your simulation result or your experimental result, it shows very soft, very smooth. But when you're switching is going to create a lot of chattering. What do you mean by switching in here? You're switching between different components?
We're switching between different, yes, we're switching between the different redundant. Let me show you specifically, for example, in this case.
But to me, okay, how are you handling the shadowing? That is my question.
Dwell time. It's a dwell time. If you see here,
yeah,
there is a minimum, a theoretically provable, the bound that I showed earlier, minimum amount of time that we need to stay into its mode to avoid issues of instability due to the switching. That's how we kind of avoid it. We make the switching slow enough with specific bounds that we have. Okay. Does it answer your question?
Yeah, yes. So switching is not fast, what you're saying.
Yes, yes. And the rate of the switching is computable. We have found how slow we need to be. At least how slow we need to be.
That's why you have this smooth curves here. Okay.
Yes, exactly. All right. So yes, as I said, we actually did investigate questions of sensor attacks, although the idea was all the notions are quite similar, because what we've done is we've based on previous work of my advisor, actually, we have transformed the observation problem into an optimal observer design problem, and we exploited duality between the linear optimal observer and then linear quadratic tracking control. So again, we have an unpredictability mechanism that switches between different sensor sets, and we have a reactive system that again takes some kind of integral Bellman error and checks whether it's zero or not. This is good because it allows for a common approach to sensor and actuator attacks. It does have the issue, which is very important, that because there is loss of this, we haven't actually looked into it too deep yet, but there is a loss of we are not able to take into account both sensor and actuator attacks at the same time with this framework, though, because there is coupling in the Bellman equations of the system. But everything else remains the same for sensor attacks. We have optimal observers with stochastic switching. We have the dwell time approach, where again, it avoids all the issues of stuttering or instabilities that come into play from switching by computable bounds on the time of the switching. And we have a sensor intrusion detection mechanism, which again looks like a Bellman tracking problem. Now, this has been here we have found also theoretical bounds for random noises in the sensors, although I have to say they are quite they were not very tight, honestly, but we still had good results. So we, for a constant bias into the observation signal, we were able to detect the attacks in an estimated angle of attack scenario. Now, what's also cool about this work is that from help by Aris Kanellopoulos, one of our undergrad members of our lab, we have been able to have to develop an integrated software that can be used by the human operator of a cyber physical system that gives in real time the switching and the detection signals and gives recommendations of actions. So that has been very interesting, and as I said, did a great job with that. Again, if there are no more questions about the moving target defense, I would like to move into one of our other main themes.
May I ask a question?
Yes. Yes.
Okay, you mentioned about stability.
Yes.
Okay, it is asymptotic stability, but how long is it taking to reach to this asymptotic stability? Because time is an important issue. During the time that system is approaching to asymptotic stability, many things can happen.
Oh yes, yes, obviously, and we can detect them. The detector does operate during transients. The switching operates during transients as well. Yes, yes, yes.
Okay, all right, thank you.
Can
I ask one more question?
Yes, of course.
Okay. There is a price for what you are trying to do. You're at one hand, you are trying to make the system complex enough to reduce the hacking. Yes. But what is the price that you are paying for it?
I mean, apart from the obvious one, which is we need more sensors and we need more actuators. So it kind of depends. This, I think, would be quite an ad hoc answer, right? Because if I have a drone and I'm claiming that I can just buy and put in a couple of more GPSs or LiDAR or what have you, I don't know about LiDAR. But, you know, if I can buy more sensing components and put them in the system, that's not much of a problem. But imagine trying to implement this into a car. I'm not able to have two sets of driving wheels, right? So this is an ad hoc question. There are some applications where this makes sense, and there are some applications where this definitely does not make sense.
All right, thank you.
Thank you for your questions. So yes, moving into the issues of prediction and human behavior that we've been talking about, we are going to take a look at what bounded rationality is right now. Now, most optimization problems in general rely on the ability of the agent to optimize perfectly. Which in the game theoretic sense, it means that the predictive abilities assume perfect optimality by its individual player and consistency of the beliefs. So not only is everyone optimal, but everyone else knows that everyone else is optimal. Everyone knows that everyone else is optimal. Those are the standing assumptions that constitute the Nash equilibrium. Now, from the beginning, so even ever since Nash published his work, there have been models of bounded rationality that have been proposed trying to show the faults and the errors of the Nash equilibrium approach. Our objective will be to exploit those bounded rationality principles and see how they can be applied into cyber-physical system security. This way, we will go beyond issues of beyond the approach of the Nash equilibrium and issues of more realistic modeling. Now, specifically the type of modeling, again, this is a huge field on its own, right? But the type of bounded rationality that we initially considered is what's called level gate thinking and cognitive hierarchy. The idea is pretty simple. It's based on the joke, oh, I know that you'll do that. I think that you think, then I think. So what happens is this. We have a limited depth of reasoning for each player, which is determined by their cognitive type. So every player draws from a distribution of intelligence, and they're assigned this level of intelligence. So a level 0 player, for example, level 0 type is completely non-strategic, whatever that means for a specific scenario. A level 1 player believes that everyone else is a level 0 player and optimally responds to the level 0 player. So by keep going through this iteration, we have that level K player optimally responds to an environment of up to level K-1 players. So we keep the optimality assumption. Everyone is optimal in what they're doing. We get rid of the belief consistency assumption. So they have wrong beliefs over what's happening in the environment. Now, we have tried to find out a way to bring this into control system and differential games. So let's consider a cyber-physical system, again, modeled by a continuous time continuous time control system. And this interacts with different adversaries. For now, we'll assume that they interact sequentially. One way to model their behavior is through a differential game by this specific quadratic in everything cost function, infinite horizon quadratic cost function. The defender minimizes and the attacker maximizes. It's pretty standard stuff. And we know that the Nash equilibrium is given by specific formulas, right? We know that we can find the minimax behavior that, again, is related to the Nash equilibrium for this scenario, and we know that this Nash inequality will hold given the specific policies. Now, as I mentioned, the infinite rationality assumption is very satisfied. We are trying to bring realistic models, and we're going to use level K thinking for this scenario. Our main idea is that bounded rationality, the way that was described before, is very closely corrected to reinforcement learning for systems. It's nothing but in principle, it's nothing but a truncated policy iteration. So let's say every player best responds to the opponent of specific thinking steps. So if we try to go through the general iteration that I mentioned, the way that it's applied here, we start by a level 0 anchor policy, a non-strategic player. As I mentioned, this is quite ad hoc. So for this control scenario, we would have the defender be completely oblivious. That is what a level 0 defender would be. They have no idea that the system might be attacked, so they just solve their optimal control problem by the usual methods, and they get the optimal controller. Now, moving on to the other player. The other player imagines that their opponent will use a naive agnostic policy, U0 in this case. So what they do is they solve a naive game, which is again given by some kind of Riccati equations. So by iterating this process for higher levels, we have the optimization of the policy under the belief that the opponent has lower level of thinking, which leads us to closed loop expressions over for a specific defender of level K, which solves iteratively Riccati equations up to their level of intelligence, and the attacker strategy that's again given by this K iteration of Riccati equations. Now, there are, of course, we have theoretical results for when this is possible to do, because it would make sense that the maximization problem, for example, of the attacker might not be solvable under certain assumptions, but we have looked into this, and in our work, our published work, we have results on that. Now, we have also, in order to solve those equations in a model-free fashion, we propose the pre-existing Q-learning algorithm. I won't delve too deep into this because this is just a tool that we use. This is we have a specific Q function that's quadratic in the actions of the agent. They have a specific closed form solution for the optimal policy, and we use approximators that are tuned based on integral Bellman errors for every level. So, and finally, by employing critical actor update laws, we have shown that every player of level K is able to learn the optimal level K policy. Now, if we go back to the sequential play with adversaries of different level, we imagine a defender that has a history of attacks over predefined periods. Those attacks are data points from players of different levels. So what they want to do is they want to estimate what kind of environment they live in. They want to estimate the distribution of intelligence in their environment, so they'll be able to predict what's going to happen. So we define an error function based on the observed attacks by the defender and the predicted attacks for each different level, and by using this is the softmax function, we were able to get, based on some previous results on behavioral economics, we have been able to model distributions of intelligence in the environment of adversarial intelligence. And as you can see, by having the system interact with different players of different levels, it is able to reach the true distribution of attackers in the environment. Now, we have an algorithmic framework for level distribution learning, where the attacker will be able to determine, as I said, the intelligence. And the reason to do that is because by using those known predictive these known models of intelligence, it will be so much easier for the defender to adapt to different players by using a database of policies. Okay, so I think okay. Again, if someone has any questions about our boundary rationality framework for differential games, please feel free to ask. All right, so moving on. We kept digging into the principles. Yes.
Yeah. You mentioned about differential bound, and then for the control, you had an equation in terms of a partial differential equation. I think it was one of your equation for U if I am
Oh,
not
you mean, excuse me?
before your simulation result.
Oh, before my simulation results.
Yeah, you remember that you had a U in terms of, yeah, right here. No, this is you solved this before this.
I know what you're talking about. You're
Okay,
talking
now of
about
course you're gonna have because it is related to
this.
this. What did you assume? Yeah, right here.
Yes.
Okay, but somehow you're assuming about V that you came up with a new control signal, optimal signal. What was that? What are your assumptions about V?
Oh, yes, yes, yes. Again, we do have the analysis for this. Every sub problem, so every level K problem, by just plugging the belief of a level K agent into their optimization problem, it is quadratic in nature, and the quadratic cost functional with linear dynamics is known to give quadratic value functions. So dvdx will be linear. That's why that's how we are able to go to this expression and all the different expressions for different levels that are linear in X.
Yeah, but is it in reality? Is it really linear?
It should be. It is a quadratic. It is a quadratic functional with linear systems, and it's not the only case where this would be problematic is in distributed, decentralized control scenarios. But this is not the case here. So yes, a quadratic cost function with a linear dynamical system will be given. The optimal behavior will be linear in the.
Okay. Thank you.
Thank you for your question. So moving on. Yes. So we have tried to do some work into some more security-oriented issues of where boundary rationality is employed, and I won't, because I think we're running a little bit out of time. I won't delve too deep into the math here because it gets weird fast. But basically, the scenario that we've been considering is an environment where a specific event takes place, and we know the event, the probability of the event being 0 or 1. It's a binary event, and we have sensors measuring this event, and the sensors can be both attacked and stochastically manipulated. They have a probability of being manipulated. So by looking into the probabilities of all of those signals that we will have here, we're trying to figure out what the number of attackers will be able to do in order to, in a decentralized fashion, manipulate the sensors in such a way such that we won't be able to know what the actual event will be. So this is a binary event with binary sensors that are manipulated by multiple attackers. So again, we have specific assumptions on how all the signals operate, binomial distributions and stuff like that. But what is important to note here is that in case of attack, what we're going to deal with is we're going to find the distributions that the attackers will choose in manipulating, in how many sensors they're manipulating. They're flipping the sign, basically. They're flipping the sign. They're flipping the sensor. Now, we assume that that this is a non-zero sum game between different interacting attackers, and each of them has a dual cost, a cost of inducing an erroneous estimate from the system side and remaining stealthy. Now, by going through some math, we have shown that the error function can be written in this way. And just a side note, in this work, we are trying to come up with predictive models of attack. So we're not dealing with the estimation strategy of the system itself. This is just a prediction model. And what we're doing is we're trying to derive this prediction model as Dirac distributions over how many sensors an attacker will try to attack. Now, By employing bound rationality as a non-equilibrium solution concept of the game, we again start from a level 0 policy, which here will be just a uniform distribution. So a level 0 attacker just randomly switches, randomly attacks a number of sensors. But every level above that has to solve a problem with this reward. Now, in terms of their belief, we again use this behavioral economic driven approach of cognitive hierarchy, which is given where the belief is given by this expression. And by going through the math, we were able to show what the best response of a level K attacker will be. So what is the distribution that an attacker would induce into the system? Now, again, the simulations here are a bit weird because there's not an easy way to find NAS equilibrium to confirm what is happening, but we have seen in general that low average intelligence induces non-equilibrium strategies. So if the players are not smart enough, they are further away from equilibrium in general. We have shown that an increase in the strategic level induces strategies where more sensors are compromised, and at limiting conditions, both in intelligence and in stealthiness. And again, we have a bunch of work of theoretical results into that in our TAC paper. We have shown convergence to the NAS equilibrium under specific scenario. Now, unfortunately, the math, this is mostly a math theoretic problem. It's a math heavy problem. So in terms of principle, I would like to move into our final approach into non-equilibrium for games and cyber-physical security by going through our dynamic deception using learning in games. Now, in this sense, we get a more abstract view of the security problem. We have a game between players, a set of players, it's with a finite set of actions, and it's with a utility that can encode the security or safety objectives. Now, there are a number of different things that we can consider here, from matrix game to bimatrix to network or polymatrix games to, of course, dynamical and inferential games, which we already talked about. Now, each of these games has been for years analyzed by different and separate solution concepts. We have NAS equilibrium solutions, which we've already mentioned. We have refinements such as subgame perfect NAS equilibria and quantal responses. And we have boundedly rational equilibria that we've already talked about. There is, however, a completely separate approach to those problems. Those are the learning solution concepts. And again, those are completely separate in principle. The players change their policies during play. There is a vast literature of different methods for those as well. The most well-known is probably Cournot adjustment or fictitious player replicator dynamics. And of course, there's reinforcement learning for those specific scenarios, which is not to be confused with reinforcement learning for just plain old control systems. And of course, they do allow for use of tools from dynamical systems and control, which is what intrigued us in the first place for that. So what is our objective? Our objective is to bridge those static and dynamic concepts. We want to take bounded rationality and transform it from a theory of bounds in action to a theory of bounds in learning. So a first approach into this problem was through this reinforcement learning algorithm, where every player has a specific memory of what's been happening in the game. They have their own utility functions and the score function that keeps memory, basically, which can be described in dynamical system theoretic terms as a simple differential equation. And every player chooses what to do based on just some kind of static choice map. Now, there has been a lot of work into this specific framework where people have talked about regularized optimal responses, right? But this is our question from a control theoretic perspective. This is a dynamical system. can an intelligent player, a player that is now able to see the dynamics of the other players, can he take advantage of the opponent's learning mechanisms? So in that sense, a smarter player will be able to understand not only what the other players play, but how they learn and adapt. So the first thing that they will need to do would be to learn the learning mechanisms of their opponents. So again, going into the mathematical framework, we employed mimicking dynamics for the intelligent player, which showed their ability to reason on the game, the way that the game evolves, and how others adapt. At first, we assumed that the player knew the utility functions of their opponents, and we came up with an approximation structure given by this description. So as you can see, we have basically the same dynamics with unknown initial conditions for the memory. So we know how the memory of the other player evolves, but we don't know what their initial biases are, and we don't know how he acts based on those biases. So that's where the tuning parameter W comes into play. Now, the intelligent player is able to observe the action of the other players, and they minimize the prediction error over what their opponents are playing and what he predicted that they would play. By getting this error signal and using a gradient descent rule on the squared error, we were given this learning structure, meta learning, as we call it, framework. So again, we have had theoretical results for this, where we showed that a player of higher cognitive ability that is able to reason about the learning dynamics is able to asymptotically learn, converge to the learning mechanism of the opponent, both in terms of their memory and in terms of their actions, in terms of their choice rule. Now, one interesting extension is to be able to have the same framework without knowing the opponent's utilities. Now, this is challenging because it requires two approximating structure, which should be tuned by one single measurement. So we only measure the actions of the player. We need to tune both the utilities, the predicted utilities, and the predicted choices. Towards this, to make things a little bit simpler, we restrict our attention to polymatrix games, which are given, where the utilities are given by this quadratic expression. And the only reason is because this is something that we were able to linearize in terms of the unknown utilities. Now again, by getting an approximating structure the same as before, but now with predicted utilities in the memory instead of the actual utilities, we employed something called propagation through time to tune the unknown and find the unknown parameters. So given a single measurement of the actions of the rest of the players, we need to learn the choice map and the utility function. It's interesting because the mathematical problems that we encountered were the same as what someone has at the tuning process of a multi-layer recurrent neural network. Because we have the error signal going through an unknown function, through a memory block, which is given by zeta dot, and through another unknown function. So that was very interesting. And indeed, by employing this dual learning structure, we have the choice map given as before, the same as before, but now we have a sigma modification of the gradient descent on the utility of the rest of the players. The problematic part here is the last term in the expression, where we introduced this back propagation through time analysis that was able to give us an auxiliary dynamical system to be used during learning. So now we have dynamics on the memory, dynamics on the tuning of the choice map, dynamics of the utility function prediction, and dynamics of the auxiliary function. Putting it all together, we were able to show that the signals will be ultimately uniformly bounded, which again is a result that we have published. Now, quickly showcasing how that would work, we considered, first of all, the known utility scenario in a two-player penny matching problem. And we can see that indeed the intelligent player is able to learn the choice map and the initial biases of the player in order to follow their memory function. We do need, as with all learning mechanisms, we do need some kind of probing, but eventually the meta-learning does work. The learning of the learning component does work. Now, in the non-utility function, our results are actually very encouraging because, again, in the two-player penny matching problem, we were able to show that the intelligent player was able to learn the utility and the choice map and the memory of the rest of the players. So those are very encouraging results, really. Now, our time is running out, as I can see. So let's just discuss some kind of future research directions that we've been thinking about. Now, first of all, for the deception, we need to, now that we have results on learning how the other players learn, we need to see how we would be able to exploit those results. We need to somehow see whether we're able to gain in the long term by knowing how the other players are learning. So we're going to use ideas from optimal control with economic reward functions to see how that would, if and how that would work. We actually are just about to finish some of our initial results on that. Going back to security, the one thing I haven't talked about is what happens in the network, the underlying network between components of a cyber physical system. So we do want to talk about problems of denial of service or jamming attacks through a dynamic game formulation. We need to figure out how we can move beyond robustification issues that most people talk about in terms of denial of service attacks for CPS, and see how we can employ the aforementioned redundancy to actually do something. What can we do? How can the defender actively secure the system? And finally, in terms of the prediction problem, we need to have higher complexity models and somehow get ideas on how dynamic intelligence works, because people are not pre-assigned levels of intelligence. As they learn, their intelligence increases. So we need to come up with ways to describe these phenomena and how we can use these predictive abilities of these phenomena, and how we can, at the end of the day, have autonomous systems collaborate or defend against human agents. And that would be all. I think I'm right on time, 1 hour and 4 seconds. Thank you all. Thank you all.
Yes, Aris, you are on time. Thank you so much. Thank you so much. Very interesting talk. I have a lot of questions, but I'm going to let others on the cyberspace to ask question. Any question? Dr. Karimuddini?
Yep, I just enjoyed the talk. Now I missed part of the beginning of the talk, but I'm hoping that I can have the rest of the talk recorded, the video recorded, and perhaps I will follow up later.
Okay, all right, good. Okay, any question from Aris? Okay, while others are thinking, okay, when you say the dynamic deception, okay, first let me just give you my definition of a deception, and then dynamic deception in my mind is a time varying problem. Yes. Deceptive problems are a difficult problem because the max and means are at the same point, and you don't know which one is which. That's why they're calling it deceptive.
Yes.
Okay, when you say dynamic deceptive, but in the formulation that you stated, your A was, again, time invariant, but dynamic deceptive, it is time varying.
Yes, yes, and there are dynamics, right? Because what we want to look into and what we want to investigate, and this is something that I am very excited about, is yes, the game might not be time varying, as you said, but what is time varying is the memory and the belief and the mental state of the opponent. So imagine a scenario where this will not work in the scenario that I'm going to describe because it's completely symmetric. So let's say we're playing rock, paper, scissors. If I know your learning algorithm, if I know how you adapt your strategy based on what you see, which is something that we are able to do with this meta learning algorithm, I can come up with a time varying profile of strategies, profile of plays over time that will drive you to specific states, mental states, that will drive you to playing specific patterns, time, time functions. So that's where the dynamic, the time varying nature comes from. We're not looking at static games. We're looking at static games playing in a repeated fashion. So we're trying to, instead of coming up with a specific action that will be the deceptive action, we're trying to come up with a time varying function that will be a deceptive function that will drive your learning mechanism where it will be most beneficial for me.
Okay.
So for example, again, this doesn't work in specifically rock, paper, scissors because of its symmetry, but if I want my opponent to play with a specific frequency, let's say rock or just rock, if I want them to play just rock, all I have to do is just keep playing scissors, right? Yeah, scissors. If I keep playing scissors, eventually, modulo the inertia of their learning, they will eventually think that, oh, well, this guy keeps playing scissors, so I should just move towards rock.
Just for your information, about 20 years ago, designing a deceptive problem is quite difficult.
Imagine.
Quite difficult. So we have a paper about 20 years ago that we can design a deceptive problem of different difficulty.
Okay.
So just look under my name. About 20 years ago, it was ICGA was the premier conference.
All right, I will definitely look into that because this is actually an interesting point, right? Obviously, not every problem can have a deceptive,
Yes,
either static or dynamic approach. Again, as I said, rock, paper, scissors doesn't. If I lose for a certain period of time, there's no way I can make that up. So characterizing problems based on their utility functions, problems where deception is possible, that's a very interesting point.
yeah, very difficult problem.
Yes.
Very difficult problem.
Yes, definitely.
Deceptive problems are difficult, especially dynamic deceptive problems.
Yes.
That's extremely difficult. All right. Now, any question from?
So, yep, I do have one question. Even though I missed part of the beginning or part of the talk, and excuse me if the question doesn't make sense, but when you get to the formulating the problem toward the middle of the talk, when you are talking about modeling the players in the form of finite state machines, sort of things. So, were you considering kind of deterministic model? How from there go to a sort of more probabilistic model, let's say even MDP or POMDP sort of things, where the situation is slightly more uncertain? Do you think that there would be some rationality to go that direction, or did you consider any sort of probabilistic sort of approach in that aspect?
So yes, thank you for your question. I haven't used MDPs per se because most of my work has been in continuous time, but the idea is the principles are basically the same. And the answer is no, but we probably should eventually. So there is a lot of work to be done in, as you said, seeing what happens when there's random noise around, right? Especially in all the prediction and the estimation of the attacker's behavior. If the dynamics themselves have noise and disturbances, then definitely this is something worth looking for. We haven't so far, but yes, you're right. This is definitely an open problem.
Thank you.
Thank you.
And on the other hand, also, is there any sort of, I mean, the continuous state is sort of things, sort of important aspect of the job, but also, is there any sort of, sorry, is there any sort of discrete actions that the players may take, or no, it is all sort of continuous actions that you were considering here?
So in our differential, actually, in all of our approaches, it has been continuous. No, we have looked into continuous problems. In our differential game scenario, they are controlled games. So basically, every attacker has k times x. So this is just a linear feedback controller, and we see how the k's, what k represents its level. In our sensor attack, our non-zero sum sensor attack scenario has been static, but again, in modeling the actions of the attacker, we have weights on Dirac distributions, so those are continuous as well, basically. And finally, we have the reinforcement learning framework that we have for the meta learning part at the end. It does consider continuous action or evolutions of mixed strategies, basically, to bring those to the dynamical systems framework. So no, we haven't looked into discrete actions. And actually, an interesting point to that would be that for the dynamical, reinforcement learning part at the end, discrete actions would give us a lot of trouble with chaotic solutions and stuff like that. But we haven't looked into that yet.
Okay, great. Thank you so much.
Continuous approach. Thank you.
Hello, Aris. It's me, Rabbi. Thank you for your nice presentation. I have one question about your tracking. And that when we are tracking, we are doing either point-to-point tracking or trajectory tracking, especially as you are using reinforcement learning to update your stage to track the system. So here is the question is that how is your time horizon? Have you considered that point-to-point tracking at the same time trajectory tracking together? Or using your reinforcement learning approach, you want to try to do the state estimations and know the policy and then make an assumptions based upon that you look forward.
I'm sorry, I didn't get the last part.
Yes, so my last part is that using the reinforcement learning approach, you are doing the state estimations and then predict and then move forward. That is how you are making the tracking.
You mean what we showed for the moving target defense framework,
yes,
right?
Correct.
Yes. So let me think. We did look into trajectory tracking specifically for the observer, right? This is an observer. So we shouldn't be thinking this in terms of an actual controller moving the system. But if you take a look, I can send you the paper if you're interested. It's a bit of an older work of my advisor. So there is the observer. Think of a Leuenberger observer. This fictitious, let's say, input that the Leuenberger gain would give you, this is given by a linear quadratic tracking problem. So the observer tracks the system, and I did try point-to-point tracking, and it worked. The problem is the simulations didn't look so cool, really, but it is doable with this reinforcement learning-like algorithm.
So your assumption here is that you are linearized your system, right? It is not
yes,
nonlinear.
Yes, this is important. This is for linear systems, and the reason this is for linear systems is because there would be there are ways to go into the nonlinear system. Like from a technological perspective, there is no reason for this not to work. If I have solved my reinforcement learning problem from offline data or what have you, right? Then obviously the Bellman equation holds. It should hold. It has to hold. It's just easier to find explicit bounds for linear systems. That's why we have focused so far on linear systems. The problematic case, which is kind of an extension of what you're asking, like the problem in the next step would be that, especially in nonlinear systems, there is a lot of like separation principles break down. So there is a lot of interconnection between, there's great interconnection between the Bellman equations of the observer and the Bellman equations of the controller. So things get really weird there. But we have focused on linear systems so far. That's why we've been able to find explicit bounds on things.
Thank you. Actually, from your simulation results, the questions comes to my mind. And I have another question about your static cognitive hierarchy.
Yes.
Here, at a certain point of time, you have said that learn the learning framework of the opponent. So when we are talking about a learning framework of the opponent, we need to think about that the action policy of the opponent. That is also somehow indeterministic, and it is not known for another person. So it is always changing with respect to time. And so as the reinforcement learning is a trial and error based approach, so its policy is also changing. Even though you are using the model free approach, its off policy makes the system somehow takes more time. So my question is specific, that how much time it takes to know the system to the opponent.
Okay, that is for the last part, right? With
Yes.
the meta learning. All right. Because for the cognitive hierarchy, we kind of did for the static problem. But in any case, I kind of see your question. Okay. This is why I mentioned that the term reinforcement learning is a little bit problematic in sometimes can be problematic, because if you take a look at the equations that we had, for example, where is it? Here, for example, here, right? Or even the actual environment. There we go. The problem is that, talking about off policy learning, right? You're thinking of a scenario when an underlying dynamical system or an MDP is into play, and we have the scenario of model, basically multi-agent reinforcement learning, right? There is an underlying dynamical system, and people act, and they have observations by the system, etc., etc. This is a different framework from the beginning. This is a framework. It's called reinforcement learning. There are a lot of things. There's a lot of work from specific communities where they refer to this as reinforcement learning, but it's not the same as the Bellman principle of optimality-driven reinforcement learning, where
yes, that is the question. That what I'm looking for. I do understand.
Yes.
I think that the rest of the thing I can understand, because it's not the actual one that the reinforcement learning people are doing. Thank you.
Yes. This is both a problem and an opportunity, in my opinion, because there is a lot of discrepancies into what people have been thinking about, and there are open problems in one community that can be solved with tools from other communities, and there's a lot of miscommunication of terms. So yeah, that was a great question. Thank you for letting me bring this up.
Thank you.
Okay, I think we have gone up 20 minutes. I'd like to thank Aris and everyone. If maybe one more short question, anyone has any? Okay, with that, we're going to thank the speaker again. Thank you so much. Thank you so much.
Thank you for having me.
Yeah, really pleasure. Thank you so much.
Thank you.
Very interesting talk. Yes.
Thank you.